Okay, let's get started. So, number one, ethanol C2H5OH will combust in air according to this equation. Is O2 oxidized in the reaction or is it reduced? Justify your answer in terms of oxidation number. So, the oxidation number of O2 here is 0. We know this because it's a diatomic element and it's all by itself. So when something's by itself, its oxidation number is 0. Over here, whenever oxygen is paired with something, its oxidation number is normally -2. Conveniently, carbon has a +4 charge, so overall we have a +4 and 2 -2's, so that will add up to 0. Again, over here, hydrogen is a +1, there's 2 hydrogens, so oxygen has a -2. Hydrogen always has a +1 unless it's with something like lithium hydride. So something from the first column, then the lithium takes the +1 and the hydrogen takes a -1. But that's not relevant for this problem. So since O is going from 0 to -2, its oxidation number is being reduced. So we would say reduced, and we would just say 0 to -2. Alright, B. When a sample of C2H5OH was combusted, the volume of CO2 gas produced was 18 liters. At this temperature and this pressure, determine the moles of CO2. So we're given volume, temperature, and pressure. So we should use the ideal gas law because we have pressure, volume, temperature. We just need to find N number of moles. Let's convert Kelvin or Celsius to Kelvin by just adding 273. And that gives us 294.7. We could solve this equation for N, since we're looking for moles, determine the number of moles, and that would just be PV over RT. We plug in all of our values, 1.03 times 18 over the R constant, 0.08206. We're going to use 0.02806 because our pressure is in ATMs. If it was in torr, we would use that other R value. And then our temperature is 294.7. You do some math, and you get 0.766 moles CO2. All right. My thing started getting a little funky here when I printed it out, but this is, I guess, C part I. Determine the volume of C2H5OH in milliliters that was combusted to produce the volume of CO2 gas collected in part B. So the C2H5 is our only source of carbon. You can see that for every 1 C2H5, we make 2 CO2s. So we could set it up. Oh, and then in B, we just found the moles of CO2s. So we could find the moles of C2H5OH of ethanol, because we have 0.766 CO2. For every 2 CO2, we make 1 ethanol, 1 C2H5OH. This would give us moles of C2H5OH. And then we could convert that to grams from there, and then to milliliters. Let's just quickly determine the molar mass of C2H5OH. Because we have moles, we'll have to go to grams, and then to milliliters. So molar mass of ethanol, carbon is 12 times 2. Plus the 6 hydrogens, so plus 6, plus the molar mass of oxygen is 16. So that gives us a molar mass of 46 grams per mole. And so we can continue this here. We have 46 grams of C2H5OH per every 1 C2H5OH. And, one more step here. Now that we're in grams, we can use the density to convert to milliliters by just flipping this around. This is 0.79 grams per 1 milliliter, so we could also say it's 1 milliliter per 0.79 grams. And I apologize, this is a multiplication sign. And that equals 22 milliliters of ethanol. Alright, let's go to C part 2. Determine the amount of heat in kilojoules that is released by the combustion reaction. So for this, when you are given amount of heat, you either want to be thinking Q equals MC delta T, or you want to be looking at Q equals delta H, enthalpy, times the moles, or reactions. So we're actually given delta H here, given negative 1270 kilojoules per reaction, per mole reaction, so it really means per reaction. And we could figure out how many reactions occurred using a little bit of stoichiometry. So again, we're going to pull that 0.766 moles of CO2, which we got from part B. So 0.766 CO2. Every one reaction takes 2 CO2s. So we can say one reaction is 2 CO2. And then times our enthalpy, which was 1270 kilojoules per reaction. Negative 1270 kilojoules. And that gives us negative 486 kilojoules. For part E, we're given the mass of air originally at this temperature. Assume that all of the heat produced by the reaction was absorbed by the air, so there's no loss of energy to anywhere else. The specific heat of air is this. Determine the final temperature of the air in the room after the combustion. So this is going to be a Q equals MC delta T problem. Our mass is 5.56. Our specific heat is 1.005. This was our Q, which we just determined, negative 486 kilojoules. We should convert that to joules. And then it's important to note, this is Q of the reaction. So that Q we determined in part, I guess this was part D, was the Q of the reaction, and we're now looking at the Q of the surroundings. So they are inverse, or not inverse, they are just the negatives of each other. So our Q of air, the energy of the air, is absorbed by the energy of the reaction. So it's just the negative sign of it. So it ends up being positive 486 kilojoules. And we could convert that to joules by just multiplying by 1,000, 486,000. Now we have all of the information we need to plug into our equation. So we'll use 486,000 as our Q. Our M was this 5.56 times 10 to the 4th. Our C was 1.005. And now delta T means final temperature minus initial. We're given the initial temperature, originally at 21.7 degrees. So we would do TF for final minus 21.7. Now this TF can just be treated like an X, just like any variable in algebra. I'm going to skip some steps and just tell you that if you work this out, your final temperature is 30.4 degrees Celsius. Let's go forward. Here we have an intermolecular force problem. Just about any time you're given all these nice Lewis structures and boiling points, you know it's going to be an intermolecular force problem. It says ethanol and dimethyl ether are provided. Which intermolecular force is responsible for the difference in boiling point? So ethanol has the higher boiling point, 78 degrees Celsius, versus dimethyl ether at -24. Now the reason that ethanol has such a high boiling point is this right here. This is a hydrogen bonded to an oxygen, which means this molecule can undergo hydrogen bonding. As a reminder, hydrogen bonding is a hydrogen bonded to an NO or F. And the actual hydrogen bonding is that hydrogen interacting with an outside NO or F. Nitrogen, oxygen, or fluorine. This cannot undergo hydrogen bonding because none of these hydrogens are connected to a nitrogen, oxygen, or fluorine. They have the same molar mass. There's 6 hydrogens, 2 carbons, so 1 oxygen. So they have the same London dispersion forces because they have the same molar mass, the same number of electrons. But this one is polar and it has hydrogen bonding. So the answer is hydrogen bonding makes ethanol stronger, and it makes ethanol have higher intermolecular forces, and to boil, to go from a liquid to a gas, you have to break intermolecular forces. So that high intermolecular force, the strong intermolecular force, would need to be overcome to go from a liquid to a gas. So that is the explanation, is you'd have to overcome that strong intermolecular force. All right, part G. A chemist wants to run the reaction and maximize the amount of C2H5OH produced. So they're trying to maximize this product. Identify 2 ways the chemist could change the reaction conditions, other than adding or removing any chemical species. So not by changing the concentration of reactants or products. So I see 2 ways that would work. You might notice this is 2 moles of gas over here, right? 1, 1, 2. And this is 1 mole of gas. So one condition that would favor the products, the C2H5, is a smaller volume. A smaller volume is going to favor less gas. So reduced volume. And I'm not going to write out the justification, but a smaller volume can, again, handle smaller amounts of gas. It prefers smaller amounts of gas. This has to do with the pressure. The pressure would increase with a smaller volume, and as such, it would shift towards the products. A second way that you could increase the formation of products is by decreasing the temperature. So the forward reaction is exothermic. Now, always remember, exothermic, exo favors low temps. Endo favors high temperatures. And this is because endo requires more energy to overcome that activation energy. So when you have a high temperature, the particles have more energy to overcome that activation energy. Whereas with exo, they don't need nearly as much energy. So the forward reaction is exothermic. The reverse reaction is endothermic. We're trying to make more products. We're trying to do more forward. So if we reduce the temperature, that would create more of the products. Those are actually the only 2 that work, aside from adding or removing any chemical species. All right, number 2, made it through number 1. Let's go. All right, particle representations, classic. All right, we're given H2O2, making 2H2O, 1O2. Particle representation of the reactants is shown below in the box on the left. In the box below on the right, draw the particle representation of all the molecules that would be produced. All right, so we're given 4 H2O2s, sorry. So it's twice this balanced equation, right? 4 H2O2, 4 H2O, and 2 O2, because we have twice the number of H2O2s as we do in this balanced equation. So that would mean we're going to make 4 H2Os and 2 O2 gases. So we'll just draw those out. This is one of our H2O. H is the dark, O is the light. And again, we're just drawing 4 of these. It doesn't say that we need to worry about orientation, so we're not going to. But if we did need to worry about it, the hydrogens should be facing the oxygens. The hydrogens on the separate molecules should be facing the oxygens on the separate molecules. And then 2 O2s, so just like that. And that's it. Shown below is a potential energy diagram for the uncatalyzed decomposition of H2O2. Great! According to the diagram, is the decomposition reaction exothermic or endothermic? Justify your answer. Okay, so if we go to the graph, we can see that reactants have a higher energy and products have a lower energy, so it's exothermic because it released energy. So exothermic. It released energy. And we could describe that more. Manganese dioxide, MnO2, is an insoluble substance that acts as a catalyst for the decomposition reaction. On the diagram above, draw a curve to represent the reaction as it occurs in the presence of MnO2. A catalyst always reduces activation energy. It doesn't reduce energy of reactants, it doesn't reduce energy of products, it only reduces activation energy. So our line would just have a lower activation energy, a smaller hill, and it would have the same energy as the reactants and products as it did before, just a lower activation energy. So catalysts only reduce activation energy. All right, a student investigates the decomposition reaction in the laboratory. The student prepares 2 small beakers, adding 20 milliliters of, all right, and one of them has, this one has the catalyst, this one does not. They both have H2O2. You can see that the mass of beaker 1 is not changing. It does not have a catalyst. The mass of beaker 2 is changing, though. The number of moles of O2 that was produced in a 60-second period. Great. So the only source of mass lost is going to be from the oxygen gas. Right? 2H2O2 is becoming a liquid and then the gas. So for these beakers to lose mass, it has to be oxygen gas. So only O2 is our source of mass lost. So let's figure out what mass of O2 was lost. We could do 43.19 minus 42.58 because we're looking at that 60-second period. That's 0.61 grams. And then from there, we could just simply convert to moles of O2. So this is 0.61 grams O2. I should have labeled that O2. And then we're going to multiply that by the molar mass of O2, which is 32 grams per mole. We'll multiply it by the reciprocal of the molar mass of O2. So 1 mole of O2 for every 32 grams of O2. We use 32 grams instead of 16 because it's O2, not just O. And that gives us 0.019 mole O2. Now it wants to know the mass of H2O2 that decomposed. How convenient that it gave us first the moles of O2, and now we have to find the mass of H2O2 that decomposed. Let's real quick check our balanced equation. That was given to us. For every 1 O2, there's 2 H2O2s. All right. So for every 1 O2, well, first we'll start with our starting value, which was 0.019 mole O2. But for every 1 O2, 2 H2O2s are used up. So now we would be in moles of H2O2, and then we just have to go to grams of H2O2 because it asks us for the mass. The molar mass of H2O2, it's just 2 plus 32 because there's 2 extra hydrogens, so 34 grams per mole. That gives us 1.3 grams H2O2. All right, forward. The student continues the experiment for an additional minute. For beaker 2, will the mass of H2O2 consumed during the second minute be greater than, less than, or equal to the mass of H2O2 consumed during the first minute? So you can see as we progress down the table, we're losing less and less mass each time. Between here and here, we're losing 0.15 grams. Between here and here, we're losing 0.12. Here and here, we're losing 0.11. 0.10 is lost here. 0.8 lost here. 0.7 lost here. So we went from losing 0.15 grams to losing just 0.7. And that trend will continue. So that's what you would say. It would be less because we're losing less and less mass as the reaction proceeds. All right, E. Based on the data, the student claims that the catalyzed reaction has 0th order kinetics. Do you agree with the student's claim? So the integrated rate law for 0th order kinetics is just it's just linear when taken against concentration, and only concentration, not the ln of the natural log of concentration, and not the inverse of concentration. This is not linear, right? We already proved that in the last problem. This is decreasing by 0.015, and now it's decreasing by 0.07. So it is not linear, so it is not 0th order. So we would disagree, and we would explain that the reaction is not 0th order because it is not constant or linear. The reaction rate is not constant. All right, the student did the experiment using more of this stuff, but it splashed out. And the student says, because we lost some liquid, the calculated number of moles of O2 produced is greater. So since our O2 moles was dependent, let's go back. If we recall, our O2 moles was dependent on mass lost, and all of a sudden we're losing more mass because we splashed, it's going to mean that the mass changed more. So we would agree with the student because the moles of O2 is dependent on mass, and we lost mass when it was splashed out, which would produce a greater number of moles of O2. All right, G. So for G, it's just write a balanced equation. There's a couple ways you could do this one. You could do a net ionic equation if you preferred, but I think the simplest approach is just to write it out as is. Okay, so the reactants are NH4, 2S2O8. This is going to be a pain to write. And H2O. And that produces H2O2 and NH4 HSO4. Excuse me. Now, the most simple way I imagine to do this would be to first start by just counting the n's. There's 2 n's here, 1 n over here, so we have to put a 2 here. Now we have 2 n's on both sides, and that also takes care of our s's. Now we have 2 s's on either side, s2 and 2s. So let's check something else. The n and the s are good. Let's see how many h's we have over here. We have 4 times 2 is 8, plus the 2 is 10 h's, and then over here we have 2 h's plus 5 times 2 So 12 H's over here, 10 H's over here. So we're going to have to double this, and that would give us 12 H's over here. If we check the oxygen is now balanced as well. So that's it. Just one NH42SO208, S208, sorry, plus 2H2O makes 1 H2O2 plus 2 NH4HSO4. All right, number 3. So for this Lewis structure, you actually have 3 different options, and they are all valid and they all work. The only thing that would not work is putting a pair of lone pairs on this S. As a reminder, S can actually handle, sulfur can handle 6 bonds. It doesn't necessarily need 6 bonds, but it can handle 6 bonds. And I believe it's phosphorus that could handle 5 bonds, or no, that's not right. I don't remember. Anyways, SO3, S and O both have 6 valence electrons. 6 times 4 is 24 valence electrons. So we just need to do a Lewis structure that gives each of these guys at least 2 bonds and has 24 valence electrons. And there's a number of combinations that work for this. I think the simplest is this. Oxygen loves to have a double bond, so why not just give it a double bond? If we count up all of these, this is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we reached our 24 valence electrons. All right, in B, predict the shape of the SO3. So there is not a lone pair on this SO3, so there's no electron repulsion. So it's going to be trigonal planar. If there was a lone pair, its shape would then be trigonal pyramidal. Its electron geometry would be tetrahedral if it had the lone pair, but its molecular geometry, it would be, again, trigonal pyramidal. Okay, under some conditions, SO3 decomposes to produce SO2 and O2. This is the reaction. It's endothermic. Under what temperature conditions will the reaction be thermodynamically favored? High temperatures, low temperatures, all temperatures, or no temperatures. If we see thermodynamically favored, we want to be thinking about delta G. Now, we're given enthalpy. We could deduce the entropy. So we're going to use the delta G equals delta H minus T delta S. Another hint that we should be using this equation is it talks about temperature, and this is a temperature-dependent equation. So our delta H is positive. Just put a little positive right there. And our change in entropy, let's see. So we go from 2 gases to 3 gases. So that is more chaotic. So I would say delta S is positive. So this is delta H is positive minus a positive delta S. So if this T delta S is big, delta G will be negative. When delta G is negative, things are thermodynamically favored. So to make this T delta S really big, really big and overall negative, we would need a high temperature. So it's only at high T's, high temperatures. And you could explain that using this equation. All right, part D. I like part D. It's pretty, it's a pretty simple problem. So let's read it. Draw an X on the time. I probably should have read this part, but I skipped it. Okay, draw an X on the time axis to show when the system first reached equilibrium. So this is time. We have partial pressures. You can see that right about here, the pressures all start to plateau. So when they first plateau, when they first reach equilibrium. So as soon as they start to plateau, that's when they first reach equilibrium. Describe the change that was made to the system at time t1. So here's time t1. We can see O2 starts decreasing slowly. SO2 has this huge spike, and SO3 starts increasing slowly. So this huge spike indicates that SO2 was added. And we know it was added because it's a uppy-downy spike, a vertical spike, whereas here, this is like a rate of change. These are rate of change for SO3 and O2. So after SO2 was added, that created a change for these other ones. So SO2 was added. After the change was made at time t1, the partial pressure of SO3 increased while the partial pressure of O2 decreased. So this has to do with Le Chatelier's principle. Let's go up to the balanced equation here. So we added, it was at equilibrium, we added SO2, and since we added more products, more reactants will be made. So SO3 is going to go up, and if we're making SO3, that consumes O2 and it consumes SO2. So that's, I don't want to write all of that, but that is the explanation for that. All right, let's go on to E. Write the expression for the equilibrium constant Kp for the reaction. So again, our balanced equation was 2SO3, and we have their equilibrium arrows, creates 2SO2 plus an O2. So our equilibrium expression, Kp, is just products over reactants. The coefficients become the exponent, so SO2 squared, but it's Kp, that's pressure, so it should be, sorry, I gotta grab my eraser here, should be the P of SO2, the pressure of SO2, times the pressure of O2 over our product, which is SO3, so the pressure of SO3 squared. For part 2, determine the value of Kp for the reaction. So we just have to find a point where the reaction was at equilibrium, deduce those pressures, and plug them into this expression. So we could do our first equilibrium, which is when it first plateaued, or the second equilibrium values. Either one is fine. I'm going to use the first equilibrium values. So O2's got a pressure of, looks like about 0.17 atms. SO2 has a pressure of about 0.33 atms, and SO3 clearly has a pressure of 0.5. So let's go down and write those out real quick. O2 was 0.17, SO2 was 0.33, and SO3 was 0.5. We'll plug all those things in. We have 0.33 squared. Again, just following this expression, SO2 was 0.33 times the pressure of O2, 0.17, over the pressure of SO3 squared, so 0.5 squared, and that gives us 0.074 as our Kp. Easy peasy, lemon squeezy. Forwards! Yay, all done with the long FRQs. Now on to the short FRQs. For number 4, identify one of the conjugate acid-base pairs in the reaction. So an acid donates hydrogen and a base accepts hydrogen. So HClO is donating a hydrogen to H2O. You can see that because HCl becomes ClO. So this is an acid. This is its conjugate base. An acid always becomes a conjugate base. And that means this H2O is a base, and it's becoming its conjugate acid. So it just says you need to identify one of the two pairs. So just pick one, or put both of them. Doesn't really matter. All right, B. Shown in the graph below is the titration curve of HClO with NaOH. Carefully draw a second curve with the same volume, 25 milliliters, and the same molarity, 0.2, HClO4 with 0.2 molar NaOH. So HClO4 is a strong acid. This is a strong acid, and HClO is a weak acid. This group of acids, the HClO, increases in strength the more O's you have, and HClO4 is the strongest one. So like HClO2 is stronger than HClO, HClO3 is stronger than HClO2, and HClO4 is the strongest of them all. So since it's a strong acid, it's going to start with a much lower pH, and that pH is going to increase slowly. But since the molarities are the same, still 0.2 molar, 0.2 molar, 0.2 molar, the equivalence point is still going to happen at 25 milliliters. But with the strong acid, strong base titration, such as HClO4 with NaOH, the equivalence point pH should rest around a pH of 7. So we're going to draw the vertical diagram, or the vertical part, crossing through that pH of 7, and then plateauing, just as it did with the first diagram. All right. Part C, a student proposes creating a buffer with NaCl4, so a base, and a strong acid. So buffers are made of weak acids and their conjugate bases, or weak bases and their conjugate acids. So a strong acid's not going to work. The reason that it's not going to work is when HClO4 becomes ClO4 minus, which is this. This is not a reversible reaction because this is such a strong acid. So if this reaction can't reverse, the ClO4 minus cannot resist addition of H plus, since it cannot accept an H and reverse this reaction. So that's not going to be a buffer. All right, number 5. In human cells, a compound known as NADH is involved in a reaction above. Yes, classic NADH, classic. All right. How many moles of electrons are transferred for each mole of O2 that reacts? This is given to us. For 1 O2, there's 4 electrons. But it wants us to, of course, justify using oxidation number. So let's do that. All right. The oxidation number of this O2 is 0 because it is all alone. The oxidation number of this oxygen is -2. And these two hydrogens are each +1. But it's -2 2 times. So it's reduced to -2, and that happens twice because it's 2H2O. So that indicates 4 electrons. All right. Calculate the electrochemical potential of the cell. We have E naught cell equals cathode minus anode. And almost always, the goal is to make E naught cell as big and positive as possible. We never, ever have to multiply E naught values by coefficients. These are standard reduction potentials, meaning they are for 1 electron, so there's no need to ever multiply these by any coefficient. So we can just plug these values into our cathode and anode, again, plugging them in such a way that maximizes E naught cell. So we could say this equals 0.815 minus -0.320, which gives us 1.135 volts. All right, part C, calculate the value of delta G for the overall reaction. So we want to calculate delta G, and we're working with electrochemical cells. So we're going to use the equation for delta G that has electrochemical cells in it, or electrochemical potential. So we have this equation, delta G equals -NFE. As a reminder, N is moles of electrons, F is Faraday's constant, and E naught is from this equation up here. We just calculated it as 1.135. So again, N moles of electrons. It was 4 moles of electrons. Faraday's constant, 96,500. And our E naught was 1.3 1.135. And that equals negative 4.38 times 10 to the 5th joules per reaction. Typically, the AP likes delta G to be in kilojoules, so we could convert that to kilojoules by just dividing by 1,000, and that would give us negative 438 kilojoules per reaction. Forwards. When the concentration of NADH increases while the concentration of NAD plus decreases, will the electrochemical will it decrease, increase, or remain the same? Justify your answer. So we're talking about, will E increase, decrease, or remain the same? And whenever you're seeing is electrochemical potential going to change, you're always going to use this equation. E equals E naught minus RT over NF ln Q. Q is just like K, the equilibrium expression, but Q is at any time, any concentration. So let's take a look. Our Q value would be products, NAD plus, over reactants, which include NADH. I'm discluding everything else, the O2, the H plus, and the 2H2O, because the problem doesn't ask about those. It only asks about NADH and NAD plus. So I'm just ignoring them for simplicity. So our Q value would be NAD plus squared over NADH. Let's just write that out so we have it with us. NAD squared over NADH squared. So if we decreased NAD plus, this top value, and increased NADH, sorry, let's back up. At standard conditions, which is E naught, these are both 1 molar. But if we decreased them, so if we decreased NAD plus, it would be less than 1. So it would be, we could just say 0.5, just for simplicity, and we'll say this increased to 1.5. We can see that Q is a fraction if we decrease NAD plus and increase NADH. So since Q is a fraction, the ln of Q would have to be less than 0. The natural log of a decimal of something less than 1 but greater than 0 is a negative value. So we would have E naught minus, this is all positive stuff, right? This is a constant. This is in Kelvin. N is moles. F is Faraday's constant. So we have a negative times a negative makes it a positive. So E plus E naught plus some stuff. So E will increase because the ln of Q is less than 0. So E naught will, just E will increase. Okay. 6. Some building materials contain small capsules filled with paraffin. No one cares. While the wax is melting, is the net flow of thermal energy from the wax to the surroundings or from the surroundings to the wax? So if something's melting, you can imagine a pot of water with some fire underneath. A pot of butter, rather. Butter. The fire is going into the butter. So thermal energy, it takes energy to melt things. So energy is going into the wax from surroundings. All right, B. Calculate the amount of thermal energy in kilojoules required to melt 15.2 grams of solid paraffin wax. Okay, so we're given mass. We're told that there's no temperature change. So the temperatures are already above the melting point of paraffin. So no temperature change. We can just use this molar heat of fusion given to us, which is given in kilojoules per mole. to find the amount of energy it would take to melt this much. So let's first find the amount of moles of paraffin wax we have. So 15.2 grams. And it gives us the molar mass as this amount of moles per, or grams per mole. So 1 mole is 282.62 grams. Grams cancels. We're left with moles of paraffin wax. And then we want to find kilojoules. So just multiply it by the thing that is in kilojoules per mole. So moles times kilojoules per mole gives us kilojoules. And this gives us the answer of 2.62 kilojoules. Sweet! All right, when paraffin wax melts, its density decreases. So we can imagine a solid like this, and is now becoming a liquid, and is like, so you can see the particles separate, right? If this was a beaker, maybe they fill the shape of the beaker, they fill the bottom of the container, so the density decreases as they spread apart. 7A. A student is given a solution of phenol red of unknown concentration. Fun stuff. The student uses a pH probe and determines the pH is 11.2. Calculate the hydrogen ion concentration in the solution of phenol red. So we have our fun little equation. pH equals negative log of H plus. We're going to use this because we're given pH and we want to find H plus. If we solve this equation for H plus, we would see that it is H plus equals 10 to the negative pH. And now we can just plug and chug. 11.2 goes in for our pH. And then we can put that into our calculator, and that gives us 6.3 times 10 to the negative 12. And whenever things are in brackets like this, this is molar, big M, moles per liter. All right, based on the calibration curve shown below, what is the concentration of the solution in micromoles per micromolar? Okay, so, or per liter, sorry, micromolar. So the student analyzes a sample set at 559 nanometers, which is the maximum absorbance for phenol red, and they measured that the absorbance was 0.35. So let's go onto our graph. 0.35 is right here. Looks like it's about a little left of center. So this is about maybe 5.4 micromolar. So that's it. That's all you have to do. It's about 5.4 micromolar. Important note, if you suck at reading graphs, do not fear. The AP test gives a range. If you got anything from 5.2 to 5.6, they said you read the graph correctly. So you got the point for that. All right, if the student makes 10 milliliters of distilled water with 10 milliliters of the sample with this diluted solution, keyword diluted here, have an absorbance greater than, less than, or equal to. Well, absorbance is directly related to concentration via Beer's law, and I forget Beer's law right now, but it is on the equation sheet. And since we are diluting the concentration, the absorbance would also decrease. We could justify it using Beer's law. It's something like absorbance is equal to this weird thing times B times C, where C is concentration and A is absorbance. So if concentration goes down, absorbance will also go down. All right, if the student measured the absorbance of the solution at a wavelength of 650 nanometers, would the absorbance be greater than, less than, or equal to the absorbance of the solution at 550 nanometers? So we read in this part here that the wavelength of 559 nanometers is the wavelength of maximal absorbance. So any other wavelength beyond 559 will have less absorbance. So it will be less because it's a different wavelength than the wavelength of maximal absorbance. And that's pretty much it. I am so proud of you guys. I love all of you, and you are going to kick booty on this AP exam.